Hello there. Are you tired of going through different tutorials and different websites in trying to understand what B-tree is and how you can perform a deletion operation in B-tree? Then this video is the right place for you. This is Uday and I am here to help you in understanding complicated data structure problems very easily. Many of the students get stuck and confuse a lot in performing deletion operation in B-tree because after deleting a node in B-tree, we end up in different situations of the tree structure wherein we have to perform specific operations like borrowing a key and merging two different siblings in order to balance the height of a tree. In this video, we will see how simple and easy it is to perform a B-tree deletion operation with example. Let us get started. B-tree deletion can be performed very similar to the binary search tree deletion operation. And after we perform the deletion operation in B-tree, we have to validate the properties of B-tree. So if any of the properties of B-tree are violated, and that is when we are going to perform some operations. And we are going to make use of these operations very importantly in B-tree. They are borrowing operation and merging operation. And I will explain in this video where we can make use of borrowing operation and where we can make use of merging operation and how they can be performed. So do watch the video till the end, wherein I'll explain all this merge operation and borrowing operations with examples and where you can apply them. And however, we are going to make use of split operation also. We have seen split operation is made use in insertion operation very importantly, but split operation is also used in deletion operation if one of the property called K-max property is exceeded or K-max property is violated. I will explain all these situations and where we are going to use them in the video. Do watch the video till the end to understand them better. Now we will see what different cases that are possible in the deletion operation in B-tree. So usually in binary search tree, the deletion operation has two different cases. One is we deleting a leaf node who are not having any child nodes, and the other is we deleting an internal node. And again, to delete an internal node, there are two different situations. One is the internal node is having only one child key or only one child node. And in this case, we tried swapping the child node with the internal node, which has to be deleted. And then we perform the deletion operation normally. And the other case is that internal node is having more than one child nodes. And in this situation, we tried replacing them with the in-order successor and then delete the internal node. If not, we can also replace that with the in-order predecessor and then we perform the deletion operation. If you're not very aware of how binary search tree deletion operation works, I already made a video on that. You can watch that video. I'll post the link in the description section and also you will be notified with the link for that video. Do watch that video if you want to understand the binary search tree deletion operation and what these three different cases are and how you can solve that for the real-time problem with examples. Now we will get back to the B tree, and here I am going to focus on deleting a leaf node because it is very similar. The other deletion operations are very similar to the binary search tree. So here we have multiple cases. So the first is the more than minimum number of keys in a node. So we are asked to delete a leaf node and wherein we have more than the required number of keys. So we know that in a B tree, we have to follow certain properties, and important property is that order M. So for example, we have a B tree whose order is M or like whose order is 4. So in a B tree, so if the order is given M equals to 4, then the properties is going to be something like this. So C max should be 4, M should be 2, and important ones are K max, so which is key maximum, which should be 3, and K minimum, which should be 1. So if you don't understand how I came up with this property rules and how I came up with these values, I've explained all this in the B-tree introduction video. You can watch that video to understand how I came up with these values very clearly. Now let us continue with this topic. And if I'm asking to delete a value called 90 in this particular B-tree, where it has to have a minimum of one key in any given node, and if you see all the nodes are having at least one key, and if I have to delete 90 here, since it is a leaf node, I can delete it directly. And after we delete 90, we are still having one key value, which is 60. So it is having an extra key. Now I don't have to worry about anything because even after deletion operation, we will still have all these properties satisfied. So here after me deleting 90, I'm still having one key, which is still satisfying the property of K minimum. So now I don't have to worry about performing any other operations and we can simply perform the deletion operation. Hope you understood this case. Now we will see what will happen if there are no extra keys in a node to delete. So for example, so this is how the tree is, and in this case we don't have the more than minimum number of keys. And in this case what we do is we try and see if there is a possibility of we borrowing from the sibling. So here after, if, for example, if we are asked to delete 60, and after we delete 60, now we are seeing is there any possibility of borrowing a key from the sibling node. So here we are going to check for the possibility of borrowing operation. So here if you see the sibling of this particular node is what? This left sibling. And here we have extra keys in the sibling. So now what we can do is we can try borrowing one from the sibling node. So here the extra key is what? 30. So I am telling 30 is an extra key is. So if it is a left sibling, we are going to go with in order predecessor. We are going to go with in order predecessor. Okay. And if it is a right sibling, we are going to borrow a in order successor, which is the smallest element in the right subtree. But if it is in order predecessor, it is going to be the bigger number in the left sibling. But we cannot replace 30 directly here. So it has to be going through the parent. So the updated tree would look something like this. So if you are not very sure how borrow operation works, I already explained this in the previous video or in the previous video. I'll share the link in the description section. Do watch that video to understand this better. Okay. So here after we borrow 30, 30 is going to take the position of parent, and the parent node is going to take the position of the problematic node. So here the problematic node is what? This node. So 50 takes its position, and 50's position is taken by the in order predecessor, which is 30. So this is how it is going to work. So I hope you understood this case also, wherein we don't have minimum number of keys in the present node, but we have extra keys in the sibling node. And in that case, we are going to make use of borrowing operation. Now we will see a different case where we do not have an extra key in the node, and also we don't have extra keys in the sibling keys or sibling nodes. So this case we don't have extra keys either in sibling and also in our node. So in this case what we are going to do, we are going to perform something called a merge operation. We will see how this merge operation works. So after we delete 50 in this particular tree, we have been asked to delete 50, and after we delete 50, now we will see if there is any possibility of borrowing from the left sibling or right sibling. So the left sibling is 20 and the right sibling is 55. We don't have extra keys in either of the siblings. So now what we do is we try performing a merge operation. Okay. So merge operation in this situation can happen either with this particular sibling or either with this sibling. Okay, merge operation can be performed either with the left sibling and parent, and we can also perform it with the right sibling and the parent. So in this case, I'm going to perform the merge operation with this left sibling. So I'm going to merge 20 and 30 and make that as a new node. So we will see how it is going to look like. Now the tree is going to look something like this. After I merge 20 and 30, the 20 and 30 is connected to the parent, which is 53 in place of 50, and 55 still same stays as it is. So this is how this merge operation works in case of there are no extra keys both in the node, deleting node, and also in the left sibling or the right sibling. It can also happen with this particular merge operation. I can also merge this and make 30 as parent node and 20 keep as left node, and 53 and 55 becomes a right child. So this is how it is going to work. Now we will see a different case. This is really confusing for many of the people. So which is level imbalance situation. So let me give you an example for this case. So for example, if I ask to delete 55 in this tree, and after deleting 55, the tree is going to look something like this. Now we don't have extra keys in the left sibling, and we do not have any right sibling for this particular node. So in this case, what we are going to do, first we have to merge this, which is what we discussed in the previous case. But after we merge this, we have a problem called level imbalance situation. So now this is a level imbalance situation. And we already know that in B tree, the important property is that all leaf nodes must be in the same level. All leaf nodes must be in the same level. But if you see, this is level 0, this is level 1, and this is level 2. Now if you see, this leaf nodes and this leaf nodes are not in the same level. So what we do in this case, we are going to perform a merge operation again. But which node should I have to merge? I am going to merge the parents of imbalanced levels. Now the parent of level 1 is what? 60. And the parent of level 2 is what? 70. Now I have to merge 60 and 70 and make that as a new parent. Now let me show you how the tree is going to change. The tree is going to change into something like this. So now 60 and 70 are merged into one node, and 20 and 53, the leaf node which we had in level 1, and level 2 leaf nodes are going to be connected same as it is. Now this is how the tree is going to change into. And now if you see, all the leaf nodes are in the same level, and all the nodes are having at least one key value, which is the property if m equals to 4, where k minimum equals to 1. So this we already know, and this is how this particular operation works. And I hope you understood what different cases that are possible in all the deletion operations. It is really important to understand how you can solve a real-time problem for B-tree deletion operation, and where you can make use of all these different cases to solve a real-time problem. Do watch next video to understand where you can make use of all these operations in order to perform deletion operations in a B-tree problem. And I have explained clearly where you can make use of these different situations, and also I have covered how you can delete an internal node and how you can delete leaf nodes and what different cases you are going to come across. Do watch that video to understand B-tree deletion operation perfectly. Understanding these operations are really important to perform deletion operation in a real-time problem for B-tree. So do subscribe to this channel if you like the content of this channel. Thank you so much. Have a wonderful day ahead. Thank you.